want to thank the organizers of the SEG workshop on full waveform inversion, filling the gaps, for the invitation to speak here today. That is an honor and a privilege for me. In terms of the title of the SEG workshop, Filling the Gaps, I think it's incumbent that we have a clear and frank and forthright discussion of what the gaps are. And I hope by the end of this brief presentation that what we see as some of the current gaps are made clearer, and that there's value in that communication. Modeling, we know what that means. If you know the medium, you generate a wave that propagates through that medium, and you can predict the wave from various modeling methods. Inversion comes in two varieties. Inversion is seeking to determine properties inside a medium from measurements of the wave field or difference in wave field between a reference and an actual wave field, and using that difference in wave field to determine the difference between reference medium and the actual medium. There are direct and indirect methods, and what does direct and indirect is like you have a quadratic equation, ax squared plus bx plus c is 0, x is minus b plus or minus. That is a direct solution. You give me a, b, and c, and on one side you have a, b, and c, and the other side you get x. An indirect method would be you take the quantity x squared plus bx plus c squared and seek a minimum. You might not even know that among the possibilities are values of x which are complex, imaginary, sometimes real, sometimes repeated. All of that, what I just said is missing. Here, it's there. That's what direct is. Examples, indicators that you're dealing with an indirect method are model matching, objective cost functions. If you see an objective or cost functions, you're doing indirect inversion. Any form of search algorithm is indirect. Iterative linear inversion is indirect. And indirect methods, another characteristic of indirect methods is usually they call upon some kind of necessary but not sufficient condition that you have a solution, like common image gather flatness. Common image gather flatness is a necessary condition for having the right velocity, but it's far from sufficient. You can satisfy a common image gather flatness and come to a long depth because many velocities, including the correct one, will satisfy it. A direct method for depth imaging with a correct velocity, using conventional or without a correct velocity, using the inverse scattering series, would not suffer that problem. There's a role for direct and indirect methods in the practical real-world application, and we'll say a few words at the end of this talk. We're going to be focusing on the direct methods. So as I said, the idea is if you have, let's say, a reflection coefficient, how do you go from a reflection coefficient as some archetype data to the changes that occurred in the medium that produced that reflection coefficient? How do you directly solve for the changes in Earth properties within some model that produce that reflection coefficient or reflection coefficients? So that's a very elementary way of talking about how a difference, in other words, let's say you had a wave that went straight through a homogeneous medium, a homogeneous elastic medium, and then you change, so suddenly it's homogeneous, and then another homogeneous elastic medium, and suddenly you get a difference in wave field from the initial wave that went straight through. This scattering theory is just perturbation theory. It relates how difference in medium properties relate to difference in wave fields. If L is the differential operator for a medium and G is its wave response, and L0 is a different medium, and G0 is its wave response, then V, L0 minus L, has the difference in properties in the two media. And the scattered wave, G minus G0, is the corresponding difference in wave field. Equation 1 is an essential message of this talk. If you come from this talk with nothing but equation 1, I will have succeeded. Equation 1 is a 100-year-old formula, which is an operator identity that relates wave field G, G0, G0, G, and V, where V represents the difference in medium properties that govern the propagation of G0 and G. This you can see simply from this operator. That form, equation 1, it's called the scattering equation or Lippmann-Schwinger equation from different applications. It doesn't care whether L, L0 are acoustic, elastic, electromagnetic, Schrödinger, whatever L and L0 are and G0 are, they satisfy that equation. That's an identity as strong and clear and true as the Pythagorean theorem for right triangles. A squared plus B squared is C squared, and this sit on similar firm ground. So that is a very important message of this talk. So from that identity, you see G is on both sides. You can go through a set of procedures where you put in for G, G0, and then put in for G, G0 plus G0V, G0. That you get a series like equation 2 from 1. Equation 2, as long as it converges, is identical to 1. 2 is identical to 1. 2 is the forward scattering series. It says you can generate the difference of wave field from as a power series in V. V squared, and so on. Its form is geometric. AR squared, giving you AR over 1 minus R, where A is G0 and the rate is VG0. So this sum has a term linear in R, quadratic in R, linear in V, quadratic in V. Just as this forward series is geometric in R, you can solve this equation for R in terms of S. As you have here, and you get a geometric series for R in terms of S. That's the inverse geometric series. That is the inverse scattering series. To realize that equal form, you needed to understand one fact. That identity, G is G0 plus G0VG. If you digest that, you realize that the series is geometric, not Taylor. Geometric series have inverses. So just as S can be written as a power series in V, V can be written as a power series in measurements of the scattered wave, G minus G0. Those terms, that series is the inverse scattering series, and it represents a direct solution. It's geometric, gives you the linear, the quadratic, the cubic. The quadratic doesn't fix the linear. The quadratic is the quadratic. And there are explicit terms, formulas for every one of those terms, V1, V2, and they are solvable directly in terms of G0. It could be water speed propagation and data. So the relationship 2 provides a geometric forward series rather than Taylor. Geometric has an inverse series. All conventional current mainstream inversion, including iterative linear inversion and FWI, are based on a Taylor series concept. And hence, the only thing that they can see is looking for iterating linear, because they can't see how you invert a Taylor series. Because in general, Taylor series do not have an inverse series. So solving a forward problem in an inverse sense is not the same as solving an inverse problem directly. And so we'll make that very clear. That is a fallacy, very common in all fields of inversion. So we have this inverse series given with this geometric analog and this is the inverse scattering series, where the role of S is in terms of D, and you have V1 linear in D, so you're getting all these different orders of V, linear, quadratic, cubic, the contribution, the cubic contribution to V, cubic in the data. We'll ask what data in a minute. That's the next essential issue. So there are 2 points of this talk. One is there is an operator identity that is unambiguous, that is as firm as any principle of mathematical physics, that says G equals G0 plus G0 VG. And that has a forward series, and it has an inverse series, and it's geometric. The second key issue or point to communicating this talk is that if you're dealing with any elastic problem, then you have to start off, here's a 2D elastic problem, isotropic. And in 2D or 1D, it's with offset data, and you get this L is a matrix, and the components phi p and phi s are coupled. There are off-diagonal terms. If you are in a PS coordinate system and you will have a homogeneous medium, then P and S are uncoupled. If you have any heterogeneity, P and S are coupled. They're not independent. They're not solved for independently. To solve for P, you must couple with S. So you have a forward series, now it's a matrix, in terms, it's just that same old geometric forward series, now with an operator. And this again is not controversial. But you see what goes on here. If you were looking for PP data, you start off P, VPP, GP. And then on this term, you would start off with GP, and then it would have all possibilities here that go in intermediate steps through P, go through S. So it requires all these components to get any one component of the data. The P data generation is not on its own. It cares about interactions in the Earth that involve P to S. The inverse series in this same form, with these operators V as written out here in space and frequency. You have this forward series. This is now the inverse series. Data is G0, V1, G0. It's matrices. The second term in the inverse series, G0, V2, G0, is G0, V1, G0, V1, G0. This couples. If you want one component of V2 PP, because you're after VPP, then you need to have all components of the data. And not only do you need it, this inverse series, which is as firm as that operator identity, tells you exactly how to use that multi-component data. It says you need multi-component data and what you do to that data to get a direct inverse. So inverse scattering is not iterative linear inversion. If you take G0, V1, G0 is D, and solve for V1 and change the reference medium, and you go through, keep updating the linear, you get a different procedure. And Jinlong, Yang, and I, we have a paper that we're submitting to SEG, and that we'll be sharing with our sponsors, showing you explicitly. Forget about elastic. Just take acoustic 1D normal instance and look at what ISS does for finding the change in properties, change in velocity at top solid compared to iterative. They don't agree, and the inverse scattering series always converges, and the iterative linear does not. So they're not equal. So iterative linear for the simplest case of where you're not in an elastic world. In an elastic world, you have to use for a direct inverse that data matrix, and you have to apply that data matrix as that direct inverse prescribes. However, what goes on is there's people have lost sight. They'll take one component, DPP, G0P, V1PP, and start inverting it, iteratively or otherwise. That's one component of a matrix. One component. And if that's your beginning and the start of your theory, you have lost sight of the entire two things. One is the operator identity between change in wave field and change in medium properties. Plus, you've lost sight of the nature of the elastic wave equation. You take the elastic wave equation and that operator identity, and it's unambiguous that the direct solution involves matrices of data and exactly in what way those matrices need to enter to get a direct nonlinear solution. If you're doing this, you're violating that identity. It's as if you were dealing with right triangles and violating the Pythagorean theorem. That's how serious it is. So you don't have the right data from the direct inverse point of view. And so if you have the right data and you do iterative linear, you have the right data but the wrong algorithm. It's not the algorithm that gives you direct inverse. So you have to have two things. The right data. Where did the right data come from? It came from the operator identity and the elastic wave equation. That said what the data needed to be. That prescribed its own requirement. And so you need the right data and you need to follow the prescription that the direct inverse says. If you don't, you have a hint of what a gap might be in your current FWI. Your whole procedure is based on some approximate modeling, updating that does not correspond to a direct inverse. And the power and message and the framework. In other words, someone would say, well, what's the use of all that that framework, that direct inverse? Why? Why? Because if you have a direct method like the quadratic equation, its solution, you know if you drop the square root of b squared minus 4ac, what you just did. A direct inverse gives you a framework for when you provide what it requires and use the algorithm that it prescribes, that in principle things should work. Now you're going to have other issues, broadband and low frequency issues. Of course you will, but at least your theory to begin with is on solid ground. That's the point here. So this is referring to this paper that Jinlong and I are writing, and you will soon get a copy of. And so if you're going to honor that relationship, then you have to have multi-component data, and you have to use it in a prescribed way that this operator identity tells you to use. It's that simple. Okay, now what if you don't have multi-component data? Well, Haiyan Zhang in her thesis showed, well, you synthesize. You see these terms where it's asking for multi-component data. You take PP and you try to estimate what those other components are. That's better than just putting zeros in. Okay, so there are compromises that we all make in the real world. We understand when you have toad streamer, you do not have multi-component data. It doesn't mean that this formalism has no value. That doesn't still give you a framework. There's a role for direct and indirect. The role for indirect is where the reality is beyond what you've written for the physics. And there is always parts of the world that are outside your equations. And that's where indirect methods have an appropriate and important and critically needed aspect. You need to be very judicious in the choice of these adaptive cost function applications, but you need them. To ignore the parts of the real world that are outside your description of physics is at your own peril. That's, in our view, the role, appropriate and essential role for indirect methods. But if within the physics that you've described, there is nothing that compares to a direct method in terms of clarity and definitiveness and value. There's a 4D application we just mentioned of Haiyan Zhang, who won a Karcher Award for this work. She was able to discriminate between pressure and fluid saturation differences using a direct nonlinear inverse from the inverse scattering series, where the differences V were not the difference between a reference and actual medium at one time, but the difference in the reservoir from one time to another. And she was able to produce a distinction between those two quantities, fluid and pressure, that linear methods that were available at that time within conical fields were unable to distinguish. So this is a set of references that gives you detail of some of the comments, gratuitous sounding, that I made in this talk. I want to thank the organizers of this Abu Dhabi 2015 SEG workshop for this wonderful opportunity, and I'm available by phone to answer any questions. I hope the message of the significance of the operator identity that describes the general relationship between the difference in medium properties and the difference in wave field, item 1, coupled with the elastic wave equation, the message that those two combined has been made clear today. Again, thank you for this opportunity. This is our group. Very happy for them, very grateful to them, and